A few weeks ago I posted a series of videos on YouTube about designing a temperature monitor using the 8595 thermocouple amplifier and a PIC microcontroller. I received a lot of feedback from YouTube viewers and EEV blog forum members, for which I am very grateful. There were a few problems with the old design and I wanted to add some features to it as well, so I've spent a bit of time and came up with revision 2 of the temperature monitor, which you can see here. Before we explore this new temperature monitor, let's review what was wrong with the old one. You cannot see the 8595 and the PIC 16F1519 because it's already inside this new temperature monitor. But one of the easiest mistakes that one can do is to start laying parts on a PCB without considering where that PCB will be installed. In this particular case, the almost square shape of the PCB makes it hard to install this PCB into a regular rectangular case, as you can see. Of course, it's possible to cut away bits of the PCB and rearrange everything, but in this case it was much easier to just desolder the main chips and solder them onto a new board. The new version uses a chip case bought from Farnell. It was probably about $2 or $3. I didn't screw it because I want to open it up later and show you the insides. That's why it's not quite closed. I've cut a prototyping board in advance and drilled holes in it, as you can see. And I've also drilled holes into the case to make sure the PCB will stay at the bottom of the case in a nice position. And I also made sure that the front panel will fit along with the connectors that tie up everything together inside the case. Another problem with the old design was that the high power consumption was too much for a regular 9-volt battery. The whole circuit used to consume up to 80-90 milliamps of power, which is a lot of current for a 9-volt battery. It's not much for a DC adapter, but quite a lot of power for a 9-volt battery. While a big chunk of that power, about 30 to 40 milliamps, was used by the 7-segment digi-display, another large chunk was used by the voltage dividers used to reduce the 8595 output and the voltage battery output to the desired levels. As the microcontroller was configured to use a 4.096 voltage reference, all the voltages coming from the battery or from the 8595 had to be under 4.096 volts. As you can see in this old schematic, the only two resistors that I had that were 1% accuracy or tolerance were 150 ohms. At that moment I didn't realize that by doing this voltage divider with such low resistance values, I would have about 300 ohms resistance between the output of this 8595 and ground. Therefore, if we go and use the Ohm's law, let's assume that the 8595 outputs about 1 volt, which is equal to about 100 degrees Celsius. So let's say we measure about 100 degrees Celsius and the output of the 8595 is 1 volt. And then we simply use Ohm's law, voltage equals current times resistance, and as we have 1 volt equals current times 300 ohms, the two 150 ohm resistors, we will have about 3.33 milliamps of power wasted in this voltage divider. Now if we go and check the datasheet for this 8595, we will see that it actually shows here usable output current, and we go to 8595A, and we see that the usable output current is plus minus 5 milliamps. So it's not such a good idea to use such low resistors, because at even 200 milliamps or under 200 degrees Celsius, I apologize, under 200 degrees Celsius we will actually go above the maximum 5 milliamps that the chip is designed to output on these two output pins. Also, as you can see here, to measure the voltage on the coming from the battery, I've used a 330 ohm resistor and a 180 ohm resistor. Now, assuming we have about 9 volts coming from the battery, we have 510 ohm resistor going to ground. So let's measure the current for this voltage divider, and we have about 18 milliamps of power wasted in this voltage divider. So not only was I using about 30 to 40 milliamps on this LCD display, on this 7-segment digit display, but there was also about 3-5 milliamps wasted here in the voltage divider for the 8595, and about 20 milliamps in this voltage divider for the 9-volt battery. It was probably not so obvious in the previous videos, but the output temperature measured, and shown on the 7-segment digit display was not that accurate. It was moving back and forth a bit. That may be the reason, this voltage divider may be the reason why that happened, along with the fact that this output terminal was not really designed for the thin wires of the thermocouple I have. In order to get rid of this terminal, I've crimped a simple 0.1 inch pitch terminal to this thermocouple, and therefore it's now easy to just plug it inside this connector and we have a good connection. It's not quite a perfect thermocouple connection. Normally you would use a proper connector, but I simply couldn't wait to receive the connectors, the proper connectors for thermocouple in the mail from Hong Kong from eBay. So this is good enough. So in the new version, in order to avoid this power consumption, I'm using two 7.5 kilo ohm resistors. So we have about 15 kilo ohm resistors between the output voltage and the ground, and therefore the power consumption is actually under 1 milliamp. Also, for the battery voltage detection, I'm using an 8.2 kilo ohm resistor and a 2.2 kilo ohm resistor, which are just 5% precision tolerance, whatever you want to call it, because it's not critical to have a very accurate reading. The output impedance of both voltage dividers is still below the 10 kilo ohm value recommended to keep the ADC of the microcontroller happy. And now both voltage dividers waste less than 1.5 milliamps in the worst case scenario. Even at 12-15 volts on the input of the 7805, we're still going to have less than about 2 milliamps wasted in this voltage divider. In the old version of this temperature monitor, I was using a TO220 7805 regulator, but in the new version I can simply use a TO92 7805 regulator, as you can see here. It's quite hard to see, but it's right there by the small capacitor right here. The LCD display used on this new version is not perfect because as you can see, if I turn it on, it requires a backlight to actually see the digits, the white digits, but it's a reasonable compromise. I bought 10 of these displays from eBay. I paid about $21 for all 10, while if you go and buy one from a store like DigiKey or Farnell, they usually cost about $5 to $10 each. A clear LCD display or a reflective one would work much better, but I'm not that worried about it because the LCD doesn't use that much power. Without any backlight, the LCD uses about 1 to 2 milliamps of power, and the backlight is simply a single white LED. And on the back of the LCD display there's a resistor of 100 ohm, which limits the current going into the backlight to about 15 to 20 milliamps depending on the quality of the LED installed on the LCD display. For a few seconds I can live with the fact that the display will use about 20 milliamps and then the power will drop to less than a few milliamps. As the power consumption of the backlight is so small, less than 20 milliamps, it was possible to simply connect the anode of the backlight directly to one of the pins in the microcontroller, as you can see in a few moments. Let me move this aside. Here we have the schematic of the new board, and you can see here that the anode of this backlight is connected directly to the pin, the output pin on this microcontroller, and the cathode is connected directly to ground. So by simply connecting it directly to a pin, it's possible to avoid using a MOSFET or a transistor to turn on and off the backlight, and we're saving board space and we're making the whole circuit simpler, easier to design. I can actually open up this box right now, and you will see that there is a jumper right here at the input of the 7805 regulator. Let me take out these cables. Here you can see the jumper, and we can connect a simple cable there and measure the current used by this whole circuit using a multimeter. We can plug this simple cable here, and then we can simply connect the multimeter probes to those wires. There we go. So now we just have to connect this back to the main board, because this connector is important. And now we can just turn on everything. Let me zoom out, and you should see in the back the multimeter showing the actual power consumption. As you can see, with the backlight enabled, we see about 18.5 milliamps of power, and as the backlight will be turned off, we can see that the multimeter will show a much lower power consumption. There we go. So the whole project uses about 7 milliamps from a 9-volt battery. Okay, let's disconnect this multimeter from the board, reconnect the jumper, and have a look at the insides of this new board. There we go. On the left side you can see the AD595 thermocouple amplifier along with a header. The first two pins in the header are voltage and ground. The next two are T- and T+, the two thermocouple wires, and the fifth pin is the negative voltage pin. If we disconnect this jumper, which is right now soldered in place because I simply couldn't find an extra jumper. If we disconnect this and feed the fifth pin with a negative voltage, we can measure negative temperatures using this 8595. At the bottom of this PCB we have a trim pot, a potentiometer. This can be anything between 10 kilo ohms and 50 kilo ohms, and this potentiometer is used to adjust the contrast on the LCD display. The middle of the trim pot is going directly to the contrast pin on the LCD display. At the top of the board we see the TO92 5 volts regulator and an input capacitor that's probably 33 or 47 microfarads, and we have a whole row of 90 degrees right angle headers. The first 5 pins are the ICSP, the programming header for the microcontroller. We have MCLR, voltage, ground and data in clock, and the following pins are the cathode and anode for backlight, the contrast, RS, read-write, enable, then voltage and ground for the LCD display, and then we have the 8 data wires for the LCD display split into 2 sets of 4 wires. So we have here the first 4 bits, we have here the 4 unused pins are the pins for serial and I2C, and the last 4 wires are the last 4 bits in the data bus, as you can see here in the schematic. The last 2 pins are actually moved from here because the PX16F1519 has port D in this order: D0, D1, D2, D3, and then we have D4, D5, D6 and D7. So these 8 pins are all part of port D. So by sending a byte to port D, we're sending a byte through all 8 wires on the LCD display. And these 2 pins are RX and TX, serial receive and transmit, which are connected along with 5 volts and ground to this bottom connector. On the far side, on the far right side of the PCB, we have the 2 inputs, one DC input for the DC jack, one input for the 9 volt battery, and then there are 2 Schottky diodes which act as a sort of reverse voltage protection. Then the 2 input voltages go into this 4-pin connector. The 2 input voltages go to the front panel, where we have a switch with 2 positions, 1 or 2, and depending on the position of the switch, one of those DC inputs is connected to the linear regulator on this side of the PCB, on this side of the board. Also, the 8595 is connected to the raw 9 volts or whatever voltage is coming through one of these 2 inputs. The button is pulled down to ground using a 1 kilo ohm resistor, but when it's pressed, it's connected to 5 volts and the signal goes to the microcontroller through this 4th wire in the first 4-pin connector. When the button is pressed for a short period of time, the backlight is turned on. If we keep it pressed for a longer period of time, about 5 seconds, this tells the microcontroller to assume the backlight is always turned on and to enable the backlight as well. If we press the button again for a few seconds, for about 5 seconds, the automatic backlight is disabled and we again have to press each time to turn the backlight on. And the last 2 pins on the front panel are simply connected to the 2 pins that are the T- and T+, the thermocouple amplifier, thermocouple pins on the 8595 chip. Let's connect everything back and start introducing some of the software improvements made to this project. Okay, in the original version, the temperature was calculated by extracting the range of temperature the millivolt value received from 8595 belonged to, and then we used a simple formula to determine the exact temperature using that minimum and maximum temperature for that range. This was good enough, but it wasn't a very nice method to determine the temperature. In this new version, I took advantage of the approximate inverse functions for type K thermocouple, which were listed in the same document that is available from this address. As you can see, there are three sets of coefficients. So it's using this formula, it's easy to simply multiply the millivolt value obtained from the 8595 with these coefficients and obtain the actual temperature with a much better accuracy and precision. And it's easy to just instead of searching in a table and seeking and retrieving data and multiplying and so on, it's simply to just do the math and obtain the temperature using a very simple formula. It looks scary, but it really isn't. So let me go ahead and actually show you how easy it is. So let's say we have 10 millivolts from the 8595, which is equal to about a few degrees Celsius. I'm not exactly, I don't know off the top of my head. But let's say we have 10 millivolts coming from the 8595. That means we have to use this set of coefficients. So we have 10 millivolt. And now we simply calculate the temperature by doing 0 plus 2.5, so D1, times 10, plus D2, times D2 is 7.86, times 10 squared, plus D3, times 10 cube, and so on, all the way to D0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it may look like you would have to do a lot of multiplications, but it's actually not that hard. Instead of multiplying the millivolt value several times each time, you can simply convert this formula to this formula. 0 plus 10 times D1 plus 10 times D2 plus 10 times and so on plus 10D9. So as you can see, we no longer have to do 10 to the power of 9, 10 to the power of 8, or the millivolt value to the power of whatever, and instead we just have to do about 8 multiplications plus the last multiplication here. So this makes it quite easy to compute the temperature value using these coefficients. The other big improvement in this new version of the temperature monitor is the addition of serial logging. These 4 pins on the front panel are 5 volts, ground, RX and TX, receive and transmit. By connecting this header to a TTL signal converter to convert the 0 and 5 volts signal from the microcontroller to a proper serial signal, for example using such a homemade converter using a max 232N and a bunch of capacitors, it's possible to connect this device to a computer or a laptop like the one here. It's a good idea to output 5 volts in ground, because this way we don't need to connect this other box to another power supply. So for example, we can simply connect the two sets of pins. We can connect the 5 volts to this converter box, and we can connect the RX and TX pins back to the microcontroller. It looks a bit ugly with this mess of cables, but it's really not that. And we can simply connect this temperature monitor to external power, and you can see that the small box is powered from the main device. We still have 0 volts because it's there's no thermocouple connected. We'll fix that in a few moments. And to connect this to a computer, we have a simple $2-3 serial to USB adapter. So I'll just turn on the laptop. And connect this serial box to the laptop. Okay, let's also connect the thermocouple. I'll turn the backlight always on, and as you can see there's about 27-29 degrees in this room right now. So now we can simply connect this laptop. We can simply start TerraTherm, select the serial port. Let me zoom in so you can see. Okay. And we also have to set up the serial port to 19200, which is the value that I've used inside the microcontroller. And now, as long as the cable is properly connected here, I may have inserted it the other way around. There we go. As you can see, the temperature monitor sends all the information to the computer. So that's all there is to it. It's quite easy to configure and to receive data to the laptop or to another computer. I'm going to go ahead and disconnect this box from the laptop because it's just taking space on this desk. There is just one more modification that I want to mention. One YouTube viewer noticed that in the source code, in the previous version of this temperature monitor, I've used division by 1023 when when converting the ADC value from the ADC to the actual millivolt value of the 8595 output or the battery voltage. And as he noticed, that is not the correct way to measure. So you may think that since we have a 10-bit ADC and we have values from 0 to 1023 and we have a 4.096 voltage reference, it will make sense that if you have a value somewhere in the middle, you can obtain the actual volts value by saying value times 4.096 divided by 1023, but that's not correct. The correct way is actually to divide by 1024, and if you want to be even more accurate, it's a good idea to add 0.5 to this value between 0 and 1023. So the actual correct way to convert the ADC reading to a voltage is to do it like this, to do volt value plus 0.5 times 4.096 divided by 1024. And if we convert this to millivolts instead of volts, we simply multiply everything by 1000, so we have 4096 without the decimal point. And now we can simply divide this by 1024, and we get V plus 0.5 times 4. Now, as we don't want to use floating point and so on, we can simply do this. 2V plus 1 over 2 times 4. So now we can simply divide this 4 with this 2, and we have 2V plus 1 times 2. So for a 4.096 voltage reference, if we want to obtain the actual millivolt value from our ADC reading, we can simply do this: 2 volts plus 1, 2V value plus 1 times 2. If we have a 2.048 volts reference, then it's a simple case of dividing by 2 or simply shifting the value 1 bit to the right. So, as you can see, by doing this trick, we don't have to divide by 1023 anymore, which is not the correct way. And I'm going to post a link under the video which explains in more detail and much better than I could on a piece of paper and in the short amount of time I have for this video. So please look below the video and check that link, and you will understand why it's better to use 1024 and why it's a good idea to add 0.5 to this ADC reading. Now I'm going to go ahead and switch to the computer display, and I'll try to show you what changed in the source code and explain if there's any need to. Here we are at the computer, and we have the project open in MPLAB X. And from the start you can see that all the 7-segment display header file and the display C file is gone, and the old temperature header file is now renamed to main header file, simply because this header file contains constants and definitions that are valid for the global project, not just the temperature C file. So I thought it would be a good idea to rename it to a better name. There are some new definitions here: backlight timeout, button long press and voltage refresh, and button light. These are related to the backlight and how often, in the case of voltage refresh, how often the battery voltage is rechecked. So let's start from the top. As we have new resistors, two 7.5K resistors, there's another ratio for the temperature, and there's also another ratio for the voltage, for the battery voltage detection. We now have a 8.2 kilo ohm resistor and a 2.2 kilo ohm resistor, but these are 5% tolerance, so they're measured as shown on the screen. They're not quite 8.2 and 2.2. After every temperature shown on display, which lasts 200 milliseconds, we have a counter in the main loop of the program. When we reach a certain threshold, for example 60, or we reach 20 or 40, we have an opportunity to do some stuff. So backlight timeout 60 simply tells that after 60 updates of the temperature on the screen, the application will turn off the backlight unless backlight is configured to be always on. If we press the button for a long period of time, for at least 20 updates or about 5 seconds, then the backlight will be always on, and this backlight timeout will be ignored. If the backlight is not always on, then after the user turns on the backlight on the LCD, after 60 updates it will turn it off. So it has about 10-15 seconds, and then the backlight will be turned off. The voltage refresh, after 40 updates on the screen, the voltage of the battery is checked again, and the information is updated on the screen. And button light simply defines which input pin is the one that receives the signal from the button. The LCD header file simply contains some definitions for the LCD display. We have the port, the data port, the 8 pins of the LCD. We have the RS, RW and enable pins, and we have the backlight, LCD backlight defined as RB4 on the microcontroller. There are also some constants defined to make life easier. And then we simply have the functions which are written in the lcd.c file. This function to initialize the LCD is the standard one, which is varied for pretty much all 2x16 or 4x16 or 2x20 LCD displays. It's the same controller or the same clone of a controller, Hitachi, old one. You will find this procedure to initialize the LCD display in lots of LCD display libraries, and you will even find it in some datasheets. For example, here we have a datasheet for a 4x16 LCD display, and you see here that the pins on this display are basically arranged in the same way as on my LCD display, just a bit more towards the center of the panel of the display of the PCB. But you can see that the arrangement is the same. We have ground, we have voltage, we have contrast, we have RS, RW, enable, the 8 input-output wires, and the backlight, cathode and anode. And if we go and see the schematic of my board, here we have the schematic. You can see that we have the backlight, cathode and anode. We have the contrast, which goes down to this trim pot. And we have RS, RW, enable, 5 volts, ground, and the first 4 wires and the last 4 wires. And we have these D0 and D1 going to these pins on the other side of the microcontroller. So these two plus these two plus these two all are part of port D on the microcontroller. Here we have the serial output, and here we have I2C, which we don't use. Okay, we have LCD data defined as port D, and we have all these RS, RW enable on port B. Now, as I said, to initialize the LCD display, it's the same procedure as on any other LCD. And if we go again into this datasheet, we can simply scroll down, and we have the instructions, which are the same for pretty much all these cheap 2x16 displays. And we also have in this datasheet instructions regarding initialization. So as you can see, in case of 8-bit interface mode, we simply have to follow this procedure. In case of 4-bit mode, if you want to use fewer wires, we can simply follow this procedure. In my case, as I have a lot of input-output pins on a microcontroller, I'm using the 8-bit interface. But if you want to, you can use 4 wires, but you have to change this function a bit. It's also possible to not use the RW read-write pin, but that I'm using that pin because I want to check if the LCD is busy and wait until the LCD is not busy to send the data. The alternative is to simply wait the minimum amount of time after each command you send to the LCD display, but this can make your application slower. So by checking if the LCD is busy before sending any command, I make sure that each command will be processed fast without any delay. So as you can see, we set the port to input to read the 8 bits coming from the LCD display. We set read-write to 1. We send the signal to the controller on the LCD display, and if everything is okay, if the LCD is busy, we should get a 1 or a 0. We should get a 1 if the LCD is still busy. As you can see in this datasheet, we go back and we have here the command read busy flag. If this db0 is 1, then it means that the LCD controller is still busy and doing stuff. So we must wait for the LCD display to finish the job. And the rest of the commands are simply the commands standardized in this data sheet. Clear display, go home, go to a particular position on the screen, turn on or off the display, move the cursor or shift the display, and so on. They're just shortcuts. As you can see, go to, write a character, and so on. Other than this, not much has changed. We're just in the temperature C file, we no longer have that long array of predefined values, and we don't seek anymore in this array. We're just using these coefficients stored in an array. We pick the particular set of coefficients, and we convert the millivolts value into the temperature using that formula, which is repeated here. So as you can see, instead of having a large array and searching for that particular range and then use a formula to determine the exact temperature, we're simply doing all this math for each time we receive a new millivolt value from the AD595 thermocouple amplifier. The only other stuff that is changed is the way the millivolt value from the ADC is converted to a particular voltage, as I've explained a few minutes ago on the piece of paper. So if we go down and we can see here that instead of dividing by 1023, we now simply multiply the value by 4 and then we add 2. And if the voltage reference is 2.048 volts, we simply shift to the right by 1, which means that the value is divided by 2. So it's much simpler and much easier to understand compared to dividing by 1023, and it's also more correct. Okay, so that's pretty much all there is to it. I also decided to use sprintf to format the floating point values into a string of characters because I was simply lazy and I have enough memory in the microcontroller to allow to introduce sprintf and all the associated functions. But if you don't have enough memory, you can simply multiply the floating point value by 100 to have 2 decimal points, and then you can simply extract each digit from the number and convert it to a character and send each character to the LCD display. It's not hard at all, it's easy. I just chose to use sprintf because it was nice and fast. This voltage show function has 2 modes, because in the first mode, that's the mode that is only once shown on the LCD display. When you start the temperature monitor, it shows on the whole screen the temperature, the voltage, and afterwards, when the voltage is rechecked every few seconds, this mode is used, in which only the first line of the LCD display is used by the voltage meter, by the battery voltage indicator. And the temperature is also shown using sprintf. It's easy. We're just adding a few spaces where needed to align those two numbers on the second row of the screen. And the logging to serial port is done by simply formatting these 3 variables into a single string, and then we send a string to the serial port. I'm using tabs simply because I want to be able to log the console, the screen, to a file, and then import that file in Excel or any other software. So by using tabs, they're basically like commas or any other separator, and it's easy to import the information. And the 2 functions related to serial port are defined in UART-C and UART-header. Here we have the init functions and the function which writes a string to the serial port, to the TX line, transmit line. This init function is quite easy to write. You just have to go in the datasheet of the microcontroller, which you can see here, and you simply go to this section related to serial transmitter and scroll down and see the exact configuration. So you have a step-by-step list of things you have to do to initialize the serial port, to enable the transmitter, to disable the receiver if you don't need it. You have to configure the baud rate generator, which you can do by going to this section. And then you have here some predefined values just in case you're too lazy to do the math by using these formulas. And in my case, I simply enabled, as you can see here, I've enabled the high-speed baud rate generator, I enabled the 16-bit baud rate generator, and since those 2 values are 1, we can simply go here and here we go. High baud rate generator and 16-bit baud rate generator, and we have a frequency of 16 megahertz. So for 19.2 bauds, 19200 bauds, which is my preferred setting, we have the value 207. So if we go and start the calculator, and we enter 207, that's CF, and we have here CF, and that's all there is to it. So we configure the baud rate, we set the input, the RX as input, transmitter as output, we disable the receiver because we don't use it in this project, enable the serial port, we configure the baud rate generator on 16-bit, high-speed baud rate generator, disable synchronous mode because we only transmit, and then we enable the transmitter. So that's all there is to it. In order to send a character on the serial output, we just have to put the character on this register and then wait until a flag is set to 1. Is transmitted? Yes. That's all. Of course, you can set up an interrupt to trigger when the character was transmitted, but at this high baud rate we can simply wait a few microseconds until that character is sent through the wire to the other device. At 19.2 kilo baud, it's very fast. It's not a problem to wait a few microseconds here. And last, we have in this main loop one counter to measure how much time has passed since the backlight was turned on, one counter to measure when is the time to recheck the battery voltage to measure the voltage again, and depending on whether the backlight is configured to be always on or always off, we have one short button press or one long button press behaving differently. And if you follow this source code here, you will understand it. It's quite easy. I don't think it's worth spending time to explain this section again. It's quite easy to understand. And this button pressed function simply does the job depending on what state the button is, if it's a short press or a long press. Okay, so that's all there is to it. I'll include the schematic in the project file. You can download the source code and the schematic from the main website, which is linked below the video. So you should have no problem checking this version of the project. Okay, so that's all there is to it. As you can see, a much better design, an improved version, fits very nicely in this small case. It can be powered from a separate power supply from a 9-volt battery. I'm quite pleased with the new result. I hope you've enjoyed this video and learned some new things. If you want to, please subscribe. I will post other videos in the near future. And thank you for watching.